Morning, Monisha.
Morning, sir.
Okay. Let's start the class. Okay. So today we're going to actually model a particular protein. I'm going to see how to model and what are the various things that are there that we can model and how to analyze the structures and all. Okay. So just a minute. Okay. I'll just share the screen. So for this particular class, as a server, we're going to use the raw beta model. Okay. So I'm sending you the link. Just click on the link. Okay. So this is actually a server which actually allows you to model a particular protein. Okay, and what's better is that this particular server is constantly monitored by the Cameo. Okay, and they fix the bug, they develop newer algorithms, they fix older algorithms, and sometimes what happens, the major thing that is lacking in protein modeling is that that while modeling you have to give the, as I've discussed, that we have to submit the algorithms, right? So your modeling product will be as good as your algorithm, right? Because if you have an algorithm that does not have very good mathematical expressions, or the mathematical expressions are not updated, then you are going to get a backdated model. Because every day people are, scientists are going through research, they're coming up with newer algorithms. Now when I say algorithms and mathematical models, what do I mean? For example, suppose we know that the protein contacts are generally established by various forces like electrostatic bonding and van der Waals interaction, hydrogen bonding, disulfide bonding, all these. Now, all of these bondings, they have a mathematical equations. Okay, but this mathematical equations is not the best or is not the optimum one. Every day, newer and newer methods are coming out, newer and newer segments are uncovered, and using those segments, using those informations, updated mathematics are coming out. So this updated mathematics should be incorporated into the algorithm to give it the best and most authentic model. So this is one of the server that actually does so. As you can see that uh, they developed the TR Rosetta model in 2022, and you can see all the bug fixes they do it. Okay, and they frequently update this, and they make sure that this particular channel is highly secure and gives a very updated message. Okay. So the first thing that we have to do is, now, first tell me, what is the most basic thing that we require for protein structure?
So basically, first we need to choose a protein. The first step should be that.
Very good. That means we need a protein sequence, right?
Yes.
So in this respect, what do you do? So first of all, we're going to simply click on this particular submit prediction. Okay. And one more thing, but before we go through, you actually have to log in. Okay. You have to make sure you are logged in, and you can see there is a register option there. You can simply register. Okay. You can register out. It's a very easy procedure. And after you register, you're going to get this particular page. You can simply click on this structure prediction and you get this page. Now, the information that you have to submit is very simple. What you have to do, you have to simply submit the target name of the protein and the protein sequence. So for this class, I have actually selected a particular protein molecule, and this is actually the hexokinase protein of Felicia. You know what is Felicia?
No, sir. Can you please repeat? Or sir, should I register now or afterwards?
No, you can register afterward. Okay, just
Okay.
take a look right now. So for this particular class, I have selected the protein hexokinase from Felicia. Do you know what is Felicia? Which animal is that?
No, sir.
It's cat. Okay, it's a cat.
Okay.
Okay. So what you have to do, first simply give the target name. Suppose I'm going to give a demo protein. Okay. And then what you have to do, you have to simply submit a protein sequence. And there are question mark that is associated after each name. You can hover your pointer to it. See, if I type in, this says that enter a target identifier. the protein sequences. You can simply start. Now in this particular respect, the protein sequence, there is a limit to the protein sequence. It starts from the minimum length is 27 and the maximum length is 2000 for the comparative modeling and the other method. As you can simply hover your pointer to this question mark and it's going to show you. The major thing that you have to do is you have to simply paste the protein sequence over here. Okay, now there are two methods of protein sequencing. One is the FASTA method, another is the normal method. Now, what is FASTA method? Do you have any idea about FASTA?
So I heard it in bioinformatics, but I currently don't remember. I think FASTA is a kind of like in URL. Basically, we have a short form of the basic link. So FASTA is kind of a short sequence of the
No,
whole
no, no, no.
big
FASTA is a format, not that. FASTA is a format, and the format is nothing but it starts with some very basically assigned characters. For example, this is a normal. The protein sequence that I have submitted is only the normal sequence, only the amino acid in a single letter code starting from N terminal ending to with a C terminal. This is the usual flow. Okay. In FASTA format, all you have to do is you give a greater than sign, and what? After the greater than sign, you can write the name of the protein. You can write something or you cannot write something. It totally depends upon you. The major thing is that the protein sequence will start from the next line. After you give the greater than sign, the protein sequence should start from the next line. This is the usual FASTA format. Okay. But in this respect, you don't have to apply the FASTA format. Only if you have to upload the file. I have already pasted the file over here, so nothing is required. But you can also have the option to upload the FASTA file. For example, if I suppose I have this particular Word document with a name, and as you can see, it starts with a greater than sign, the name of the protein and the protein itself. Suppose if I need to upload that particular page, then I have to choose over here. And while uploading, you have to upload the FASTA file. That means you have to write down in such order. Okay, give a greater than sign and then start the protein sequence from the next in line. Only that's it, nothing else. Okay, is this part clear?
Yes, sir.
Very good. Okay, so now is the major part where we choose what to do with the sequence. So this is the sequence, suppose, that I want to model. This is the sequence that I want to model. Okay, very good. But now, how would I model? Remember, in the earlier classes, we discussed about the different ways of protein modeling. There is can you name one or two such methods?
Yes, sir. Like we learned about that backbone prediction, and that you were talking about. That
Backbone
loop
prediction is
model.
a general method, but
Yes.
general workflow. But what is the name of the methods? There were three methods that we discussed.
Sir, exactly I don't remember the name, but like I remember the steps that you said that
Okay,
loop
the
ancient
major
prediction.
first thing is that, okay, so let's learn. The first thing is the AB, that is the ab initio method. Okay, so what is ab initio method? You can simply hover your pointer to understand what is ab initio. But generally, what is ab initio method? Ab initio method means predicting the protein structure only using the sequence information. Only using the sequence information. Only using the amino acid chemical properties and the physical properties, you can predict the structure of the protein. This is the ab initio method. Clear? So if I need
Yes,
to
sir.
predict my protein structure using ab initio method, then I'm going to select this option over here. I'm going to check this box, the AB box, the ab initio method. Okay. So after ab initio method, what is the other option that we have? We have homology modeling. Okay. Now, homology modeling is also known as comparative modeling. Why? Because I am comparing my protein structure with the structure of some other proteins. Now, what other proteins? Now, generally, there are several proteins whose structures are solved, which is experimentally solved. So, when we do or when we select the comparative modeling, what do? We try to find a homologue for this particular protein for our protein from the list of the proteins that are already been solved, and that thing is the server is going to do automatically. Okay, the server automatically is going to predict the structure based upon the already solved structure and give you a result. Now, currently, homology model is the better method. Why? Because here, since I have already checking it or I'm comparing it with an already solved structure, the accuracy of my solved protein increases by a lot. Okay, though in natural condition in our body, protein follows the ab initio method to fold, but the model, the hypothesis, the algorithm, or the mathematics that we have till now is not yet updated to mimic the natural condition that we live in. It fails to mimic that. It is not that much updated. It is not that much validated. Okay, so we rely on homology modeling more to predict the structure of a particular protein. Okay. So if I select this, if I want to follow the homology modeling method, then what to do? I simply click this CM method, the comparative modeling method, and that's it. Now, as you know that while I am selecting this particular protein, now sometimes what might happen, suppose I know that this protein already has a homologue. So this particular protein, the demo protein, the protein that I have named as demo protein, suppose this protein already has a homologue. For example, this protein is a hexokinase of Felicia, cat, right? Hexokinase element, enzyme of cat. Now, the hexokinase of our body that human has, the hexokinase protein that belongs to human, the structure of that protein is already solved. Now we know that this is the same, since this is the same protein, these are homologues. So to predict the protein of one structure, I can easily ensure that to check the hexokinase structure of human, because if I check that structure, then I know those two structures would be highly similar and the accuracy of my modeling increases. This is simply like predicting the facial structure of one person with respect to its twins. If they are twins, they already look similar. So if I know one twin, if I know one of the twin pair, then I know how the other will look like. Okay. And since I know that already the hexagonals of human looks like this, so the other structure is going to look like that. There might be some dissimilarities. Obviously, the twins also have some certain dissimilarities, like the complexion of the skin might be a little fairer or darker. The hair might be a little, the texture of hair might be different. Okay, the height might be different. So there are some other differences that are there, and that will be there because they are homologues that are not exactly the same structure. So that will be there. But then that particular thing is actually assessed by the algorithm or the modeling servers. Okay, they do it automatically. So if you already know that you have a structure like that, then you can submit the template structure to this. So and then you can let them know that use this template to solve the structure, or you can simply rely upon the modeling. You can rely upon the raw data server to predict and configure their own. But again, suppose today you went to Mars, or people went to Moon and they are going to Mars, right? So suppose from Mars they have found a certain bacterial species. They came across a particular species and they want to isolate the proteins there. Okay, because that particular bacteria is living in Mars. So I need to know what kind of protein that they have. Now, if I isolate a protein from that particular bacteria living in Mars, then I have no way to compare the structure because we are living in completely different environmental circumstances. Now, in that respect, the ab initio modeling method would be much more sanguine. That would be much more better. That would make more sense. Okay, clear? So it actually
Yes.
depends upon the type of protein that you want to predict, what kind of protein you are predicting, what is your research goal. So these things actually matter before selecting a particular option. Now, The server, they also have developed another method, and that is known as Rosetta Fold. Now Rosetta Fold is the newest method, and it has an artificial intelligence system that is inbuilt into it. So what is Rosetta Fold? Now see, every day lakhs and lakhs of people are using this particular server to predict their protein structure. Every day lakhs and lakhs of people are predicting structure using this server. Okay, so every day what happens, they predict, the server gets a sequence, it processes the sequence, it uploads the model, and it can understand people are selecting which model, because it generally gives us an output 4 models. Okay, so among 4 models we have to select one model, or we can select any of them. It depends upon us which to select, though they gave a particular response like that which to select, but it depends upon us. Now if we do that, let me shorten the sequence a little bit, it becomes easier to predict. Okay, so if I do that, or if the server does that, now this Rosetta Fold is actually an algorithm that is inbuilt into it, which understands what kind of structure is being submitted and what kind of model is being preferred by the other scientists. So using this as a tool, they have used the Rosetta Fold, where it uses the comparative modeling method, it uses the ab initio method, but it also uses, or it also checks which scientist is downloading which structure, so as to, this is a machine learning method, so as to learn what kind of sequence yields what kind of structure. Okay, so this is the newest method. The Rosetta Fold is the newest method and gives you the most updated result. But again, sometimes you might feel that yes, among the lakhs of people submitting the data, 80% of the people might be dumb, so they might not be selecting the best structure. You might think that, and if you think that, then obviously shift to comparative modeling method to predict the structure and all. Okay, now
So,
it is, yes,
I have a question over
yeah,
here.
sure,
Sir, for this Rosetta Fold method,
yeah.
sir, they are both using the comparative method and the ab initio method. Like it's a combination of both,
Yeah,
right?
it's actually a combination of both, because they are not focusing on what kind of, because suppose today I'm uploading a structure and I have used comparative method model to predict a structure. Suppose today again you have submitted another structure and you have used ab initio method to predict a model. Okay, so like this, people are simply submitting something and they are selecting a method to predict the structure. Okay, so when they're doing it, they're getting a structure. Okay, they're getting a structure. So this Rosetta Fold understands, or it remembers, which sequence leads to what structure that is being preferred. It does not see whether comparative method or ab initio method is being followed. It checks, if I have this sequence, suppose this particular sequence, if I have this PPP RPLPT, suppose this particular domain is present in a lot of different proteins, and it is seeing that lot of people who are downloading the structure, generally this domain is assigned a alpha helix structure. Suppose the domain has been assigned an alpha helix structure or a beta sheet structure, but most of the people are downloading the alpha helix structure for this particular domain. So it understands, it remembers that this particular domain should be given the alpha helix structure because that is preferred. Okay,
Yes, sir.
so like that it remembers. And yes, for this they use both comparative method as well as ab initio method for the prediction. Suppose in some part you already have a structure whose certain part is present, a small motif. There are several motifs, right? You know motifs, right? There are several motifs that are very common. For example, the AB motif. AB motif is present in a lot of different proteins, and AB motif has a particular strand orientation. It has a particular type of loops. So that particular fold, it is already well structured. So if you get that particular motif, it automatically assigns that structure to this particular motif. Okay, so like that it does the motif based search and give you the result. Clear?
Yes, sir.
Okay, any more question?
No, sir.
Okay, fantastic. So in this respect, there is again, when I am giving the AB method or CM method, see there are two panels that are opening up. One is the open constraint panel, another is the open fragment panel. Now what is this? Now, what is constant panel? Now, sometime while predicting the structure, it is we do not only depend upon the server to model the protein. Sometimes we use other methods like NMR spectroscopy or X-ray crystallography to predict the structure. Okay. Now, in NMR crystallography, in NMR spectroscopy, what happens? Generally, if you have to solve a protein of high molecular weight, then it becomes really difficult to solve the structure. So what do? We can simply find out certain distances between that. Uh, Sometimes we find out, just a minute. Yes. So what we do is we use NMR spectroscopy, and NMR spectroscopic sometimes give us a result or give us some idea about the protein structure. What it says that sometimes information like this, but the third amino acid is connected to fifth amino acid, or the fourth amino acid is connected to the ninth amino acid. This kind of information comes up. Okay. Whenever such information comes up, then we can incorporate those information because these are experimentally verified information, right? For example, see, suppose through NMR spectroscopy I came to understand that this particular second arginine is connected to, suppose, 10th arginine. Okay, so this is one of the information that I have verified experimentally. So what would I do? I would simply allow, I am going to simply upload that particular fragment. I am going to open the constant panel. I am to understand and say them that this is the fragment, that these two amino acids are connected, and these are connected either by the harmonic function or by the Gaussian function, or it is connected by a van der Waals interaction, and this is the distance. Suppose 3 angstrom is the distance between these two amino acids. So these information are there that we can incorporate. But remember, this is only for the people who experimentally verifies certain informations. Okay, only if you have certain information, then you can upload it to make the structure more robust. Because if I'm telling that this arginine 2 and 3 should, or arginine 2 and 4, or arginine 2 and 10 must be connected, so whatever happens, they are going to maintain that particular connection, arginine 2 and 10, and it is going to fold the proteins around that. So that would be a much more verified structure. So there is also an option like that you can use. But obviously, you are going to use that provided you have already carried out NMR spectroscopy or extra crystallography with this particular protein. Okay, and if you have not done anything, then obviously nothing, no problem at all. You don't have to do anything. You don't have to upload any fragment panel or constant panel. Okay, simply take the method that you want to predict. And there is also another method, that is predict domains. The predict domains does not, it only predicts the protein domains. How many domains that we have? Do we have a zinc finger motif? We have a AB motif. What kind of motif this particular protein has? The predict domain only predicts the domain of the protein. Why this is important? Because each of the domain is assigned with certain characteristics. For example, the zinc finger motif is generally present, found in the enzymes carrying out the catalysis, specifically in the NADPH binding region. The zinc finger is specifically found in the proteins which interacts with NADPH. So if my protein has a zinc finger binding motif, then I know that this particular protein has something to do with NADPH binding. So we can also assign some sort of, or we can guess the function of the protein if it is not already known. Clear?
Yes, sir.
So these are the things that we can actually do. And after that, what you have to do? Simple. 3 plus 2 equal to what? It is 5. And then simply click on submit. Then the job is going to get submitted. And once the job is submitted, then it is you are going to get a job ID, and it's going to send you a mail. Once the modeling is complete, it's going to send you a mail stating that this job has completed, take a look into it. Or in your own time, you can simply come back again and take a look into the structure. Okay, for example, see, once I click on Q, how many jobs are there? So see, this many jobs are currently running, this many jobs are currently running. See, all are been submitted on 7th August, 6th August, 6th August, and these are all completed. These expeditions are all completed. See, a single, this is Lizhen 2105. Either he or she has submitted almost 20 different structures. So various people are submitting the structures, and you can see all the deadline and all. Okay, so people uses this server very hugely. Okay, and you can see how many. So in this particular, see, I have submitted a particular protein and it is active. It is yet to be over. So you can get to know whether you have, if it is completed, it's going to give you the IDs that this is completed. Okay. Okay, so currently, see, let me show you how the data looks like. So this particular structure is completed. Once it is complete, it's going to send you a mail, and once you open the mail, you are going to get something like this. Okay, this is the output model, output. Okay, so how to check the output? Generally, what are the different things that are there? First, it's going to give you the idea and all the sequence that you have submitted, etc., etc., and it is going to give you 5 models. See, this is the model 1, this is the model 1. Okay, this is the first model that you can see. So this particular is the alpha helix, and rest of them are, these are the beta sheets that I can know of. Yes, okay, and this is the particular part. Then again you have another model, that is model 2. This is the second model that they have predicted. Almost looks similar, but there are certain differences. Okay, and this is model 3. Okay, like that 4 to 5 different models have been given. Now it's your job to select the which is your best model. Okay, now how to select it? See, again in this particular left hand corner you get to see an RMSD plot. What is RMSD? Root means square deviation. Okay, however in this x wide aspect you can get to see that Armstrong error estimate, that means how much error is present while predicting that particular amino acid's position. For example, in the model 1, you see the first amino acid, see whichever residue that I am highlighting here, that same residue gets highlighted over here. See, this is serine 1A and this is serine 1A. Get to know? So what is this? Is the error. That means 6 angstrom error is assigned to this particular residue. That means what is the error now? The lower the error, the more confident you are. Correct. If it is a pretty good model, should it contain more errors or less error?
So less errors.
Less error. That's right. So that is why you get to see there is less error. So how much error is there? It is 1.66.58. There are two things that are showing over here, 1, 6.58. One is the residue number and 6.5 is the error rate. So this is the error rate that is associated with serine. Again, for the second glutamine, error is increasing 7.27, 8.13. Like that it is increasing and it is reaching the top at 10.65. And then again it is coming down, and again it is predicting the structure for that. For this you see the error rate is 0.7, 0.67, 0.94. That means this particular part is pretty sure to have this structure only, because the error is very less. So that means it is pretty confident that this particular domain has a structure like this. The only error is for this particular domain, and it is an error. I can pretty sure see that this is an error because no structure, never a proteins. Now you might say that how do you know? I can say by experience, because no structure has a structure like that where a particular helix simply points outside. Okay, it generally folds inside. So if I have to check now, this model is actually based upon the way they understand or the way they find out the protein. Now see the model 5. the serine has an error rate of 11.96. So see, the error rate is pretty high in model 5, whereas the error rate, starting error rate was pretty low, right? It was 6.58. The highest was actually 10.55 for tyrosine. Over here you can see it is starting from the 12. That means the error rate is pretty high over there. Okay, generally. So using this method, using this method we understand, or we can predict what structure do we have, and how much the error rates are actually there. Sorry. Okay, clear? So suppose
Yes, sir.
now I want to dive down. Suppose I want to download the model 1. It pretty much seems like the model 1 is actually the best model. But then if you see the model 1, the model 2 is also giving it a pretty close combat. Why? Because it is starting from 8, but it is not going beyond 8. Whereas model 1 was actually passing 8, and lot of structures were having error rate above 8. Okay, lot of structures. But over here the model 2, it is starting from 8 of course, but it is not going beyond 8, and then it is slowly coming down. So this is a much more solid structure compared to the model 1. Okay, compared to model 1. Now suppose I want to download this particular model, and you can also see the other color method. You can color it by error estimate. The more error, see in this respect what happens, this particular domain, the domain which is blue in color has the lowest error. The domain which is highest error is colored in red. See, this particular part is colored in red, so that means that is the highest error. What I have, because I have colored it by error estimate. Okay, and this particular part has high, it also has a high error but lower than that, that's why it has a yellow color, whereas blue color signifies the lowest error. Okay, so in model 1 again, if I go to model 1, this particular loop, so it is pretty much sure that this particular loop contains the highest error. Okay, but now suppose I want to download this structure, then you can simply click on this download option over here. You click on this download option, and the entire chain or this particular model 1 gets downloaded. Okay, and again there are also, do you want to download the all coordinates, or you want to download the coordinate with less than 5 angstrom error? Always download the all coordinate error to see the method. And see, this structure has been, you also get to see the confidence. The confidence score is 0.8. Now what is confidence? Now generally the confidence score varies from 0 to 1. Higher the value, better is the structure model. Okay, so in this respect it has a 0.8 confidence. That means this is pretty much good score. The closer to 1, the better the structure. Okay, so this structure is folded pretty good. Only this particular domain is this particular loop is actually creating a problem, but that should go away once you model or you simulate the structure. Once you simulate the structure, this particular method, this particular error goes away, because you need to minimize the structure, you need to simulate the structure, and that the particular thing goes away. Okay, and then you can simply click on it and download all coordinates, then that particular coordinate can get downloaded. See, it has been downloaded, the full model. And if you have PyMol installed, then you can simply click on the open file, and it's going to open up through PyMol, and we can visualize the structure. Okay, but in PyMol we can do other things also. That's the talk of a different day, where in the last class we discussed how this is actually the structure of the protein. The protein that has been modeled, this is actually the structure. Okay, see, these are the beta sheets, as I was telling you. This is the alpha helix, these are the beta sheets, and these are the loops. Okay, so this is how you actually model a particular protein, but obviously we have to analyze the structure. We can see the structures also. There are various ways to look at the structure using PyMol, and that's the one thing that we're going to do the next day. Okay, okay, so now any question?
Yes, sir.
Yes.
Actually, you said that I understood up to this that we have to choose the perfect model
Yeah,
according to the graph, and we will see how much error is this. I understood up to that.
yeah.
And after downloading, you said we can just take it to PyMol. And so my question is, like, when I opened the PyMol after installation,
Yeah,
I saw it kind of seems to me like coding. So it's something related to coding.
it is. It seems to you like,
Like there is a coding screen and
no,
we
no,
have
no,
to
no,
code.
nothing coding. The thing that PyMol is actually a viewer. Okay, it's actually a viewer. You simply need to view the structure. It is a structural viewer. Nothing. No coding is required. Okay.
Okay, sir.
A simple click with mouse is going to do all the things.
Okay, sir. Like, sir, we already predicted the structure of the protein
Yeah.
in this specific application. Sir, then what will be the function of pymol in our
Pymol
work?
is used for viewing purpose. For example, take a look into over here. Now, over here, are you understanding which is beta sheet?
No, sir, it is not very clear
It's not
because
very
look,
clear.
two data
Yes, that
sheets
is the
are
thing. It is
overlapping.
not at all clear. Suppose I want to check how, in which direction, or in which direction the arginine is pointing. Can you see any side chain over here?
No, sir.
So how would I know if the arginine is pointing outside or it is positioning inside?
Okay, so pymol is for like.
Pymol is there to understand that. Simply take a look. Now I have all the, see, I can see all the side chains. How now this particular side chain, suppose see this particular side chain is actually pointing outside. Very good. But again, this side chain is pointing inside, right? This is pointing inside. But without pymol, it is really difficult to predict which is focusing which side, because sometimes this residue has very importance in ligand binding or protein-protein interaction and all these things. Okay, so
Okay, so
this
we
is
will
used
be
for
having a
viewing.
detailed structure
To give a
through pymol.
yes, to get a detailed structural viewing, you need to have pymol. You can predict the structure, but you can't only submit. Suppose I have already predicted the structure, but suppose you need to submit to a thesis. You can't simply give this. Can you simply give this as a structure?
No, sir.
Because it's not a very good image. But over here, I can see a very good image. Again, what is the energy dimension of this particular method? What is the energy dimension? Or which residue is which residue? Suppose this is the residue. What number residue is this? Correct. So
Okay,
these are
sir.
the things that we can do through Pine. Okay. We can also understand the surface. We can see the ligand binding site. We can predict the ligand binding site and all those things using this Pine. Okay.
Yes, sir. I got it now.
Yeah. Okay. So that is the importance. This particular thing shows you, but Pymol allows you to investigate into a more detailed in the atomistic manner.
So, sir, then using pymol, we will be getting a detailed structure,
Yeah.
and we can totally get the idea of the protein
We can
binding
totally,
site
yes.
and the function of that specific protein and
Not the
everything.
function of the protein. That is only for viewing purpose. Uh, Only for viewing purpose, not to understand the function of the protein, but to see the structure of the protein in a more detailed manner.
Okay, sir. So that will
To
be our
save the
last step.
images, yes, that will be the last task. Also, we can save
Right?
images.
Okay. That will be the last step of our protein
Yes, yes,
structure
yes,
prediction.
yes.
Okay.
Uh, and yes, that will be all.
And sir, when will be our next class?
Okay. Our next class would be tomorrow morning at 8 a.m. Okay, in the morning.
Okay, sir. Okay.
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 Okay. I'll also update on you. I'm also going to write to you on the Telegram group. But tomorrow morning at 8 a.m. we're going to have the next class.
Okay, sir.
Okay. Thank you then.
Thank you, sir.
Sure.